All right, so this is going to cover hypothesis testing using the one sample t-test. Just as a reminder, your second midterm, which covers the topics 6 through 10, is going to be at the end of this week or section. Make sure you've done the correlation regression review quiz and are really strong on z-tests as well, correlation and regression and probability. All right, so now we're going to start doing the real stuff, which is actually using t-tests rather than z-tests. We start with z because it's simple. Okay. And this first, we're going to review what we learned last week, the null hypothesis, which is the assumption of no effect, what we want to disprove. The alternative is the same as the researcher's hypothesis. What the researcher thinks is going to be the fact is the opposite of the null, and that there is an effect, and we are trying to find evidence of this, right? Alpha level, which we must set before beginning our data collection. That's our type 1 error rate. This just is how unlikely a sample result has to be to establish reasonable doubt about the null hypothesis. And then we have two options for our statistical decision-making process. We reject the null when the probability of obtaining our result given the null hypothesis is less than alpha, or we can fail to reject. And that's when the probability of results is greater than or equal to the value specified by our alpha level. So the results would not be surprising enough if the null were true. So hypothesis testing steps. We state the null and the alternative. The null is always no effect, always has an equal sign in it somewhere, either equal to or greater than or equal to or less than or equal to. We set our decision criteria, state the decision rule. For example, reject if z greater than 1.96 or p less than 0.05. Okay. We calculate our test statistic. We learned how to calculate z last topic. And then we compare this test statistic to the value of z for alpha level, right? We look at our decision rule, reject if z more extreme than 1.96, right? Then you have to describe your results in language that anyone could understand. Okay, plain English means no statistical jargon, no saying correlation or statistically significant and so forth. Just say what happened, right? So we started with the one sample z-test last topic. We just compared a sample mean against a hypothesized population mean. Okay, to do a z-test, we have to know the population parameters, both the standard deviation and the mean, okay? And we plug them into this formula. Pretty simple. But the problem is you have to know the population standard deviation. Also assumes a normal distribution, okay? The population standard deviation is almost never available, right? So you can't even do SPSS, a z-test on SPSS, unless they've updated it recently, right? But you don't need to, they're pretty simple. This means that we would have to collect tons and tons and tons of data to be able to accurately estimate the sigma or the population standard deviation, right? With a normal distribution, which is not always the case, right? And because we're taking samples, this kind of defeats the purpose, right? So we have a new strategy to talk about. This dates back to William Gossett, and he was, like many of the early researchers into agriculture, he wanted to yield best yielding strains of barley, right? And he discovered or revealed a distribution that allows us to estimate the mean of a population when sample sizes are small, right? This involves estimating the population standard deviation and a t distribution, which is based on sample size. The t-test, which is often called student's t-test, replaces z-test when sample size is small. Now, when I did statistics, I did math statistics, and the rule was if the sample size was smaller than 30, you use the t-test. But we use the t-test for everything. This is because not everything meets the assumption. Most data is not normally distributed and so forth. We use t-tests for correlation. For example, the test of the correlation coefficient, which I talked a little bit about last week, is a t-test. The slope of the regression analyses is a t-test. Almost everything. We're going to learn more advanced procedures, and really it's a whole bunch of t-tests, right? Why students? Because Gossett's employer didn't want his employees to publish their work, right? Okay, so there are three different t-tests we're going to be covering. The first is the one sample test. It's very similar to z-test. It's not actually not used that frequently in research and psychology, but it's useful. It's for comparing a sample mean against a hypothesized population mean. We don't know the parameters, right? Then we'll move on to the independent samples t-test. This is for comparing means between two separate groups. This means between groups of different people. And finally, we'll talk about the paired samples, also called related samples or correlated mean t-tests, for comparing two groups that include the same people. For example, pre-test, post-test designs, or anything where you're comparing values on two variables for the same people, same person. Same person does two tests, two different tests, or the same tests at different times, and so forth. These have different formula and different considerations. So how does T work? Uses a different table. We're going to look at that. So here is the formula for T. It's the mean of the sample minus the hypothesized population mean, right? Divided by the standard error of the mean, which is the standard deviation of the sample divided by the square root of n. Okay, this is an estimate of the population standard deviation, right? So that's a one sample T right here. This is a one sample T Z formula, and you see that it's very, very similar, right? The only difference is because we do not know the population standard deviation, we estimate it, okay? We estimate it based on our sample standard deviation, right? So Z and probability are always the same, no matter what your sample size, whereas the T value depends on the sample size, okay? The T distribution is just the distribution of all possible values of T computed for random sample means selected from the raw score population described by the null hypothesis, okay? Depends on sample size, and the degrees of freedom, okay, are used to calculate the critical value of T for the rejection region. Degrees of freedom are always going to be n-1 for a one sample t-test. So let's look a little bit at this table. This is an old table. Okay, you actually aren't going to have to use tables, but it's important to understand what's going on. Okay, so first I want you to notice that where it says level of significance for a one-tailed test. Let me get a little pen here. Okay. So right here is the degrees of freedom. This is just the sample size minus 1. So if our sample size is 11, our degrees of freedom is 10, right? And here we have level of significance for a one-tailed test, level of significance for a two-tailed test, right? So you have to go over to where you set your alpha value, right? So if you have an alpha value of 0.05, okay, and you have 5 participants, okay, your critical value would be 5 minus 1, which is 4. So you go over here, your critical value would be 2.776, and you will reject the null if T greater than 2.776, right? Okay, if it's two-tailed test, of course, you get to split this. So for a two-tailed test, remember, you have to split it for a two-tailed test. And for a one-tailed test, it's all in one direction, right? So for a one-tailed test, okay, alpha level 0.05, okay, we go and we also see we have 5 people. So we have n-1 for degrees of freedom is 4. For a one-tailed test, we reject if T greater than 2.13. 2, if our hypothesis is that it will be greater. If our hypothesis is that it will be less than, then we reject if T less than negative 2.132. All right, so let's clear that and keep going. Okay, you choose one or two-tailed. It's just what I went over. Okay, next you have to select your alpha level, right? So here's an example, right? Degrees of freedom equals 6, that'll be 7 people. Alpha 5, two-tailed, 2.447. Okay, so pretty simple. All right, assumptions for a one-tailed test, random sample of interval ratio scores. Okay, you need interval ratio here. The raw score population forms a normal distribution. And then you have to estimate the standard deviation of that population by computing the sample standard deviation. Your t-value, the critical value is the one you look up in the table. The observed value is the one you calculate by hand, or SPSS gives you a test statistic, okay? And it's referred to as either T observed or T obtained, depending on what text you're using. I believe our current text calls it T obtained, but it's the same thing. Okay, it's the one you calculate, whereas the critical value is just like with C, the one you look up in a table, right? Or SPSS does that automatically. Okay, this is the same for Z, for F, or chi-squared, which we'll talk about later. So how do we calculate T for one sample? Well, it's very, very similar to calculating Z, right? This is just the estimated standard error of the mean, since we don't know the actual one, right? And then standard deviation, we know how to do the standard deviation. We'll be using SPSS and hand calculations for this. So let's look at some SPSS output now. So for example, we might wonder if reading affects people's performance on a test of social cognition, the RMET or EYES test, which we've spoken about before. So we know from a lot of research that in general, population mean RMET or EYES test scores is 26, right? So we want to know if people who read, right? If you bring people into the lab and you have them read something and then you test them on the EYES test, you want to know if they differ, right? So if we're wondering if they differ, it's always a two-tailed test. So our null hypothesis is that it's the same as the population mean, that people who read are just the same as everybody else, right? So this would be mu equals to 26. And our research or alternative hypothesis is just that the mean is not 26. We can choose an alpha of 0.05, and you know what? That 0 should not be in front of this. 0 should not be there. I'm going to have to correct that PowerPoint, right? We'll leave it there for now. So then we run a one sample test with SPSS, which I tell you how to do in your instructional video, right? And we can see that T value is right here, right? We get the degrees of freedom, which is just n minus 1. So we know there are 226 participants here. And SPSS gives the p-values for one-sided and two-sided tests. We're interested in two-sided because this is a non-directional hypothesis, right? It also gives you the mean difference. So we can say participants did better on the EYES test after reading fiction. And the formal notation is T with the degrees of freedom in parentheses equals 3, because you round to 2 decimal places here, right? P equals 0.003. In other words, reading improves social cognition. All right, that's where the p-value is from. Okay, so here is the full output, right? It gives you the statistics, it gives you the mean for our sample. It gives a mean for a sample, which is right here. N is 226, so here degrees of freedom equals n minus 1, right? Right, okay. It also gives you what we call an effect size, and we'll look at Cohen's d for this class, okay? This is just the difference between the means. In this case, it's the mean of the sample versus the mean of the population in terms of standard deviations. You can think of it this way, right? So 0.20. All right, there's that degrees of freedom, n minus 1, okay? Mean difference. This is just subtracting the hypothesized null from our actual mean, right? And if we want to calculate it by hand, we do exactly the same thing, right? Okay, then we calculate T by dividing that mean difference by the standard error of the mean, the estimated standard error of the mean, which, if you will notice, hang on here, like so, this right here, right, is right here, standard error of the mean, all right? You see that? This is the mean difference right there, okay? All right. T. Plain English, people are better at social cognition after reading. All right, again, Cohen's d is the effect size reported for comparisons between two means It's just the size of the difference between the means standardized, okay? So our full reporting formally would be participants did better on the eyes test after reading fiction, T parentheses, 225, which is the degrees of freedom, equals 3, P equals a 0.003, and D equals 0.20. Okay, there you go. So SPSS also gives you confidence intervals, right? So this is the estimate, the range of values where we can expect the true difference in the population to lie anywhere from 0.32 to 1.55. Because it does not include 0, we can reject the null hypothesis. We can look at confidence intervals to make our decision, our statistical decision as well. If it includes 0, we fail to reject the null because that will be the difference would be 0, right? If it does not include 0, we reject the null hypothesis. SPSS also gives us confidence intervals around the effect size. So we could say that effect in the population, the difference between the means may vary from 0.07 to 0.33, right? From not very big, but it is there. Okay, I'm going to pause now, and then we will continue in the second recording.